Okay, it is 3:02, so we will wait for a few more minutes for someone, for the people to join. Okay, so I think voice is audible. So today we will proceed with today's session now. Am I audible? I hope I am audible. Hello. So since this is an interactive session, so uh, I would request everyone to introduce themselves. So can you please introduce yourself? Okay, so let me share the PPT. Welcome to this chemical crystallography course. So, by Professor Chaudhary from Ansar Mohali. So, this is probably the second week of your course. So, since your first assignment is due by I think 10th August, so there is still time for your submission of the first assignment. So, I will not be discussing the assignment this week because since there is still many of you might yet be submitting it after this. So today I will not discuss assignment 1 or assignment 2. So we will start the assignment discussion from next week. My name is Ishita. I'm from NPTEL Kolkata. So in this portal, so you must be familiar with this portal by now. And so if you have any questions, if you have any questions about the course, about the video lectures anytime, so you can ask the questions here in this ask a question tab, so via email. So when you email, so me and the professor, so we can see your questions and then we will be able to reply to you. So when you ask something and if it is relevant, so then we will reply in the reply all mode, so that the others who can also have that question so in mind, so they will also get the answer to that. So please feel free to ask questions. So we have already received some questions here, and so they're all very good questions, so we are trying to answer them. So you can ask your questions here in this ask a question tab. So although we will be meeting here every Saturday, but any time of the week, so you can ask the question, and as and when we open the portal, we can look here and we will try to answer them. So sometimes it may take some time, like maybe 2 to 3 days, but be sure that you keep checking the portal, and when you get the answer, so you please let us know. And if you have any follow-up question to that, then you can ask the same here. So then the thing which we are discussing is X-ray crystallography, X-ray diffraction. So we have learned till now about the symmetry and the manner in which atoms or molecules they arrange in a crystal, and basically so about this diffraction. So why is this X-ray diffraction method so special and so popular? Because using this X-ray diffraction method, we can view atoms in a molecule which are at very short distances away from each other, like in angstrom level. So we all know that the famous techniques which we use in our lives are like NMR or mass spectrometry or IR spectroscopy. So all that they give information about the molecules. However, there is some restriction to them. So what is the restriction? The restriction is that suppose we have a molecule and we want to know the absolute configuration of that molecule, then it is very difficult to understand that from say NMR or even from IR. So from IR we can get information about the molecular vibrations, but not about say the absolute configuration of a molecule, whether it is capital R, whether it is R or S. So if we want to know about the absolute configuration, we have to take the help of X-ray crystallography. And also another important thing is the bond lengths and the bond angles. So if we want to know, so we know that for example carbon, so it has 4 centers, then it will be in a tetrahedral arrangement. But what exactly is the bond angle? Then if we have a alkyne, C triple bond C, and then the other end is free, and then there is a methyl group or a methyl group or maybe a phenyl group, but what is the angle which that phenyl group is making with the sp hybridized carbon. So to know the bond angle, so all these very specific details we can get the information from X-ray crystallography. Hence X-ray crystallography is very important. Anyway, so let us go back to here. So how does X-ray crystallography work? So basically, so we will learn about this in the later classes. So let me turn. Okay. So we have a crystal, so which is of very small size. We shine X-rays upon it, and then there is a phenomena which is diffraction. So there is this diffraction, and we get these diffraction spots on a detector, and then we collect all these diffraction spots. We collect the intensity of the diffraction spots, and then with the help of a computer and a lot of mathematics, the person who is called as a crystallographer, they plot it, they try to understand the 3D electron density, and from there they understand the configuration of the atoms. So it is just like we use a magnifying lens to see a small object in a bigger way, to understand it, to magnify it. In the same way, X-ray diffraction is kind of similar to that. We are using X-rays to understand what is inside a very small object. So we know that the basis of X-ray crystallography is the Bragg's law, and so we all know what Bragg's law is. So basically Bragg's law is given as n lambda is equal to 2d sine theta. So here theta is what? Theta is the angle. So this is the angle theta. What is theta? It is basically the angle of incidence or the angle of reflection. D is the interplanar distance between the consecutive h-scale planes. When we are talking about a specific h-scale plane, we have lambda as the wavelength, and we have the order of reflection as n. So when we have a parallel set of planes like this, and then when X-rays are shined upon the planes which constitute our sample, this is a more schematic diagram. So this is our sample. So what is our sample? Our sample is a crystal in which there are many different kind of planes which contain the atoms in different arrangements. So when there is X-ray, it shines. So we have an angle of incidence, and then the X-rays are diffracted by the sample in this manner, and then this whole angle is 2 theta, which is the angle of diffraction. So what is 2 theta? 2 theta is the angle of diffraction, and what is the angle of diffraction is the angle which the angle between this diffracted beam and the direction of the incident beam. Alright, so this is a very common thing which many students do not understand, the difference between theta and 2 theta. So here is theta, but when we plot the PXRD pattern, we plot as 2 theta, because 2 theta is the angle of diffraction. So here, as you can see, the D, what is D? D is the interplanar distance between two planes here, and it can also be written as D with a suffix subscript H, K and L to designate that the distance between these two planes is THL. We can have another set of planes, right? So this is a crystal which can have planes like this, and then the crystal can also have planes like this. Then when the X-ray is hitting here and going out, then this is also a D, but this is some different DHKL. So this can be H prime, K prime, L prime. So this distance will be different from this distance. Like this, there can be many, a large number of planes in a crystal, and each set of planes will have their own interplanar distance d between them. It is not like there is only one set of planes in a crystal. So a crystal can have a huge number of planes, and then each of the set of planes will have their own interplanar distance. So this is the Bragg's law. So go back to my answer. So we have the Bragg's law, so where n lambda is equal to 2d sine theta, and what is the restriction in Bragg's law? The restriction in Bragg's law is that n can only be equal to 1, 2, 3, 4 or 6. There is no 5. So what is this n actually? This n is basically the you can call it like the principal axis. Okay. What about n equal to 5? Why is here it is n is not included? Because n is also an integer like 1, 2, 3, 4 and 6. So why n is excluded from here? Right, so this is the question. So in crystals, so there is, so if we talk about symmetry, so there is symmetry in molecules. There is a molecular symmetry, then there is crystal symmetry. So if we talk about a molecule, Okay. So suppose this is a simple hydrogen molecule. So you can rotate it infinite number of times, right? Uh, if you rotate it by full 360 degrees, like 360 by 1, then you will get the same thing. Now if you 60 by n, if you take as n of n equal to 2, 1, then 2, then 180. This is the hydrogen molecule. If you rotate it by 180 degrees, we will get the same. If you rotate by, it will be the same. It can go up to actually infinity. So there is C1, there is C2, C3, all the way up to C infinity. So this is molecular symmetry. All this is about molecular symmetry. But when we talk about crystallographic symmetry, so crystallographic symmetry is actually different from molecular symmetry. In crystallographic symmetry, we do not have all the integers like we can have in case of molecular symmetry. Now let us see why. Right, so this has already been taught to you by Professor in his weekly videos, but still just to kind of recapitulate. So if we consider a point, consider any lattice point P here. So what we will do, we will translate. Why? Because translational symmetry is the basic fundamental symmetry of a crystal, of a lattice. Because in order to have a lattice, you need to have translational symmetry. Without translational symmetry, you basically cannot form a lattice, you basically cannot form a crystal. Hence, you cannot do anything without translational symmetry. So, it is the most fundamental aspect. So, let us suppose that there is a lattice point here, and after this repeating distance of A, we get this another lattice point Q. So, this P and Q are the two lattice points. Now, if we rotate it, rotate this lattice point up by a certain angle, it can be any angle, right? If we rotate it, we will get another lattice point here, which I have designated as Q prime. Now similarly, this point can also be rotated to get this point. Now if we connect this whole thing, what can we understand? We can understand that this distance is A, which is kind of which is kind of a lattice parameter. So if this distance is A, then the distance between P prime and Q prime will have to be some integral multiple of A, because A is the lattice parameter. So this distance will have to be some integral multiple of A in order to construct a lattice, because of the phenomenon of translational symmetry. So if we consider this whole distance as L, then this L will have to be equal to some integer m multiplied by A. So now if we drop a perpendicular from here and a perpendicular from here, then we can understand from basic mathematics that if this distance is a, this distance will also be a, right? So if these two distances are equal and they are right angles, so this is hello, Yashwant. So can you hear me? Okay. Yeah, yes, yes, afternoon. Really? Okay, but it is given in the portal, right? Okay. No, no, it's okay. So, have you submitted your assignment? Hmm. Okay. Okay. So, I think you have to submit. Yes. Yes. So, which part you want to focus upon? Okay. So, you are from where? You are from where? Okay. Okay. So, means you are which year student? Okay. Okay. Means PhD first year. PhD first year. Okay. Okay. Fine. So you want to learn from some. Mm-hmm. Okay. Okay. So you know a lot. So you know about mass. You know about NMR and SEM. So you know a lot. Yeah. Okay. So what is your research area? So what is your research? What is your research area? Okay. Okay. So you have joined under some guide. Okay. 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 Srinivas. I think I. Okay. Oh, yeah, okay. Yeah, sure. So, can you just give me your email ID? I will email you because I have some books in my library, in my lab library. So, I also work on crystals, so which are very good. I have gone through them, but I do not remember the name and author name uh, right now. Yeah, so I will. You can post. You can in the chat box. You can give me your email ID. I will note it down. Oh, actually, I was talking about the Google Meet chat box simply. We are in a Google Meet now, right? Yeah, yeah. So in that chat box, huh? So let me note it. I can see P dot. Ah, okay. Yeah. So we were in the middle of the class basically. So in this session, so I was talking about the fivefold symmetry and also have you gone through that? No, in week one. So you can see my screen. Yeah. So Bragg's law you have read, na? Uh, yeah. So you know Bragg's law, and then you know about what? Can you tell me what is n? Number of? Hmm. Law? Yes. Yes. What do you mean by number of entities? So if this is the this is a schematic of Bragg's law. So what do you mean by entity? So you understand this picture nicely, right? So you can tell me what is. Yes. Okay. So Bragg's law is n lambda equals to 2d sine theta. So you will find this in the video also, but just to recap. So for in order to get a diffraction spot, we need to get a constructive interference, and to get a constructive interference, what is the criteria? You know that path difference should be an integral multiple of the wavelength. So from there, with some mathematics, we take this path difference and then we equate it and yes. So Yashwant, right? Yeah. So with the help of some mathematics, we arrive at this formula. Okay. Now n here basically represents the order. Okay. So here what we were talking about is the order of diffraction. So you know about molecular symmetry, right? Yeah, so you know that. So here what I was talking about, so it is like a hydrogen. So if we talk about a hydrogen molecule, then we can rotate this to get the similar structure, right? This is all about symmetry. So we have this, yeah. So this can have this has a C2 symmetry. So we have this N, but if we have a very planar molecule, if we have a linear diatomic molecule, then we can rotate it infinite number of times. We will get similar structure always, right? So this means that this N here, it does not have any restriction. It can go on from 1 to infinity. but this is about molecular symmetry. But when we come to crystals, so in crystals, when we talk about crystallographic symmetry, so there is some restriction on this n. Okay, so why is that? So there is also a mathematics theory behind it, so we will go into that. But basically we have some restriction on this n, in that it can only take these following numbers for a crystal. So what is a crystal? A crystal is basically a regular arrangement of molecules or ions or atoms or whatever. So it is a basically regular arrangement. It has a periodicity, and the most important thing for periodicity is translational symmetry, right? So in order to make a crystal, we always need to have a translational symmetry. So this is what we were here actually. So we were talking about, let me start again. So we were here. So if we have a lattice point here, okay, P, and then after translating it by distance A, suppose we generate another lattice point here. So now so we have these 2 points. Now let us rotate this point by some angle. This can be any angle, we will come to it later. So after rotating it by some angle, we will generate another point here. So let us name it Q prime. So this distance and this distance will be the same. I mean PQ, P and Q prime. Why? Because it is the same distance. We are just rotating it. Okay. So we can do this for similar thing for this point also. Now the new 2 points we get. So this P prime and this Q prime. So this also will have that translational symmetry relation because they fall in the same lattice, right? So when they have so now this distance between these 2 new points is P prime and Q prime. If we call it as L, then this L will have to be some integral multiple of this lattice parameter A. Why? Because since it is in the same lattice. So if it is some integral multiple of A, so now if we look at here, so what we will do, we will drop 2 perpendiculars here like this, then we will understand this becomes a kind of square. So this, if this is distance is A, then this distance is also A. Okay, now if we, so actually you will get the whole thing in the video, okay, in the first week itself. So this question, that why crystals cannot have a 5-fold rotational symmetry. Okay, so you will get this in detail, the professor has taught it. So I am just here for recapitulation, that if you rotate it by any angle, so we know 2 pi is the whole angle, so 2 pi by n. If this is the angle in which you are rotating, then if this is 90 degree, the remaining angle will be 2 pi by n minus 90, and then sine of this angle. So if we take sine of this angle, so it will be this distance divided by this distance like this. And then after working out a few steps, if you want, I can show you with pen and paper. It is very simple, and you will also get that in the video, so I did not make it. So if you go through with the sine formula and the same thing, what you will get is that this distance, this m, will equate to this sine. The sine of 2 pi by n minus 90. Now the thing is, we will simply have to put different values of n and see what this m comes out to be. Since this m has to be an integer, so whenever we get something which is a non-integer, it means it will violate the crystallographic symmetry, and we cannot have that fold rotation in case of a crystal lattice. So when we begin with n equals to 1, so we will put 1 here, we will get minus 2, which is an integer value. For n equal to 2, we will get sine 90, that is 1 multiplied by 2, and again an integer value. For 3 also we will get integer value. For 4 also we will get 0. but still it is not an irrational number, right? But when we put n equal to 5, we will get sine of 18 degrees. So which is in its okay. So which is a non-integer value. So this is why this five-fold rotation is not possible in crystallographic symmetry. So did you get it? Hello? Yeah, so it is like if you take pentagons, right? You cannot arrange them. There will always be some void, right? Uh, you cannot fill the gap. So now the question is that is it really so? So do you think that then a crystal will never have a five-fold rotational symmetry, or is it possible? It is what? No, but in a pure crystal, so we do not have distortions. We have a regular, yeah. But then what if I, hmm, yeah, but what if, right, only single crystal, exactly. Hmm. But what if I tell you that there can be fivefold symmetry in crystals, but this which actually violates crystallography? So actually there is a person who found out that there are some crystals which are showing this fivefold symmetry. And then when he presented his work, then the other scientists, they basically told him to go and read a basic crystallographic book. But later that actually earned him a Nobel Prize. So you are understanding. So he showed that a crystal can have a fivefold symmetry. So I want to ask you that how do you think it is possible? No. See, so what is a crystal? So crystal by definition is a periodic arrangement of atoms. So a crystal is made up of unit cells, and these unit cells repeat in three dimensions to give the crystal. So this periodicity or the translational symmetry is the defining symmetry of a crystal. Now we come to a special class of crystals which is known as quasi-crystals. So you work with polymer and all, so you know. So glass. So what is glass? So it does not have this 3D periodicity, this regular arrangement, right? So now we come to crystals. So what is a regular crystal? A regular crystal, so it is dense, it has a regular arrangement, and it is periodic in nature. Now the special class of crystals is the quasi-crystals, which have fivefold symmetry like this, but it is not periodic. So it is also dense like ordinary crystals. It is regular, so this five folds, but it is not periodic in nature. So this is is the person who found it. So he found it in 1984. Okay, so when he was working in the US, he is basically an Israeli scientist. When he was working in the US, he found that a certain alloy of magnesium and aluminum, as far as I can remember, so it was magnesium aluminum, they are giving these five-fold symmetries diffraction spots under the X-ray machine. And when he found it, so it was in 1982, and the paper he published was, I think, in 1984. And then the people told him that this is like totally wrong, there must be some mistake, you should read a basic crystallographic book, because this five-fold symmetry actually violates the law of crystallography. So you can you can listen to his interview on YouTube. So if you just type this in YouTube, you will get the interview. So it is actually very interesting. You should understand it. And since you are a research scholar, so it will also give you new insights and a different way of thinking. Okay, wait. Is it opening in your laptop or computer? So you watch it, it will be very interesting. So yeah, so thank you. And then if you have any questions, you can ask, or I will close this session. Yeah, yeah, sure. So as I was in the beginning, I was showing. So I hope you know that in the portal, so there is this ask a question tab. So here you can ask questions. Okay, so which date have you asked? Oh, okay, 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 okay. So we will see it, me and the professor. So we will see it and then we will reply. Okay. Hmm. No, no, don't. Yeah, no, no, don't say these are very important, strong words, no? So you should not use them just like that. You should use them when they're really, absolutely it's necessary or something. So we will meet again next week. Okay. Thank you.